Our world thrives on energy, powering everything from smartphones to electric vehicles. As we demand more from our devices, traditional batteries sometimes fall short. This is where supercapacitors, also known as ultracapacitors, enter the scene. These energy storage devices bridge the gap between conventional capacitors and batteries, offering unique advantages. Supercapacitors excel at rapidly storing and releasing large amounts of energy, making them ideal for applications requiring quick bursts of power. Imagine a world where your phone charges in seconds and electric cars recharge as quickly as it takes to fill a gas tank. This is the promise of supercapacitors, revolutionizing energy storage with their incredible capabilities. But how do we unlock their full potential and ensure optimal performance? The answer lies in rigorous testing, and step testing emerges as a crucial technique to evaluate their characteristics. Supercapacitors store energy electrostatically, accumulating ions at the interface between an electrode and an electrolyte. This mechanism differs from batteries, which rely on chemical reactions for energy storage. The unique storage mechanism of supercapacitors allows them to charge and discharge much faster than batteries. Furthermore, they can withstand hundreds of thousands, even millions of charge-discharge cycles without significant degradation, unlike batteries with limited lifespans. These characteristics make supercapacitors a game-changer in the world of energy storage, paving the way for a more efficient and sustainable future. Step testing is a crucial process in understanding the true capabilities of a supercapacitor. It involves applying a sudden electrical load, like a step function, to the device and observing its response. Think of it as a stress test for supercapacitors. By analyzing how the voltage and current change over time, engineers gain valuable insights into the device's performance under various conditions. During a step test, the supercapacitor is first charged to a specific voltage. Then an electronic load is suddenly connected, mimicking a real-world energy demand. The supercapacitor discharges through the load, and the voltage drop across the device is carefully monitored over time. The rate of voltage decay provides critical information about the supercapacitor's internal resistance and overall performance. This controlled discharge process unveils important characteristics of the supercapacitor, including its capacitance, internal resistance, and energy storage capacity. By analyzing the voltage and current profiles during the step test, engineers can determine how well the supercapacitor will perform in real-world applications. This information is vital for optimizing the design and operation of supercapacitors in various systems, from electric vehicles to renewable energy grids. One of the most significant advantages of supercapacitors is their remarkable power output. Power output refers to the rate at which a supercapacitor can deliver energy, and it's a critical factor in applications requiring quick bursts of power. Step testing helps quantify this power output, providing valuable data for system design and optimization. During a step test, the sudden discharge through the electronic load allows engineers to calculate the peak power delivered by the supercapacitor. This peak power is directly related to the internal resistance of the device. A lower internal resistance translates to a higher peak power as less energy is lost as heat within the supercapacitor. Imagine a supercapacitor powering an electric bus. When the bus needs to accelerate rapidly from a stop, the supercapacitor must deliver a significant amount of power in a short time. Step testing allows engineers to determine if a particular supercapacitor can meet the power demands of such an application. By understanding the power output characteristics, they can select the most suitable supercapacitor for the job, ensuring optimal performance and efficiency. Internal resistance is a crucial factor influencing the performance of a supercapacitor. It represents the opposition to the flow of current within the device, and it directly affects its efficiency. Step testing plays a vital role in determining the internal resistance of a supercapacitor, allowing engineers to assess its overall performance. During a step test, the voltage drop across the supercapacitor is directly proportional to its internal resistance. A higher internal resistance leads to a larger voltage drop, indicating that more energy is lost as heat within the device. This energy loss reduces the overall efficiency of the supercapacitor, limiting its ability to deliver stored energy effectively. Imagine two supercapacitors with the same capacitance but different internal resistances. The supercapacitor with lower internal resistance will be more efficient in storing and delivering energy. It will experience less energy loss as heat, resulting in a higher overall energy efficiency. Step testing allows engineers to identify and select supercapacitors with lower internal resistance, ensuring optimal performance for a given application.